All right, let's get started. So as a reminder, I've got this like live question thing. So if any questions come up during the lecture, it's the last lecture. I'll put this in the first slide. So, but it'll come up periodically when I ask for questions. But if you don't want to ask questions by raising your hand, if you'd rather ask them just by submitting them electronically, you can go to this URL, bit.ly/475 questions. You can submit questions. You can also vote them up if you see other questions that you like. I'll try to monitor those questions during the lecture, and if I don't catch them during the lecture, and I see one that seems to be a common one that I think should have been addressed, then I'll try to address it on Canvas or in a future lecture. So that's how that should kind of go down here. If I doubt there's a whole lot of questions from last lecture, and we're going to do a little recap, so I'll just move ahead. So quick reminders, for those working ahead, homework B1 and Lab 2 are available online. So B1 doesn't actually get formally assigned until Tuesday of next week, but if you want to work ahead, the first half of B1 is very similar to the lab you just did, Lab 1, where you come up with entities and et cetera, actually that we'll talk about today, and the second half is a hand simulation example, which is actually very similar to Lab 2. So those kind of work together. Chapter 2 is the kind of the content we'll be covering next week. And then there's an ICA, a Canvas activity. Again, you can drop like 7 of these, but if you just want to sort of keep track of the material moving forward, this is an auto-graded kind of quiz-like thing that is due before lecture B2. So it's over the material we've covered so far, as well as the material that will go into lecture B2 that hopefully you're reading ahead for. So that's what's sort of the outline of what's moving forward. And today, last lecture, we talked about modeling in general, and now we're going to start introducing simulation modeling, which is the major focus of this course. So from last time, we basically talked about how industrial and systems engineers have to deal with coming up with engineering for these complex mixtures of people and technology. And really, there is no science to understand the complexity behind these systems. And so it's our job to do both the science and the engineering. And so the engineering part, we're kind of well familiar about that. If you give us a model, we can then develop engineering designs that optimize with respect to that model. But then the real question is what happens if you don't have that model? In most other engineering, those models are given to us. We have the ideal gas law. It's a model that was been developed by scientists and is given to us that we can come up with clever ways to use that. In our case, we often don't have the models, and so we have to develop them ourselves. And so this class is about developing those types of models, which is why we have to focus on understanding what is a model and how accurate do models need to be. So we talked about how there should be some general definition of a model that takes into account fashion models as well as the model, the Bohr model of an atom and the model of an electron, as well as animal models. And my claim was that anything that comes under this name model answers a what-if question, or or at least helps you answer a what-if question. So that's my general kind of definition of a model, is it's something that answers or tries to answer a what-if question. And the goal here is not for the model to be a perfect, accurate representation of the world, but to do this. And so the model might leave a lot of things out from the real world, but if it gives us the ability to move forward in the real world, it's still a useful model. So we could, the real world can itself be a model. We can build technology, deploy it onto the world, and just see what happens and learn from that. And that happens a lot, right? So we do learn a lot from technology that we deploy. But the hope is if we can build these artificial models that say we implement inside these computers, that we can not only, maybe learn about these systems before we actually subject people to them, but maybe we'll actually be able to build more generalizable models inside simulation. So we might leave things out of simulation that aren't, that don't necessarily come all the way up to reality. But by doing so, we might actually make our models more generalizable. So rather than going to the local Chipotle and coming up with a solution that's customized just for that Chipotle, if we build a model of a fast food restaurant that leaves some details out that maybe are in any real restaurant, we might be able to come up with a more general principle that works across all fast food restaurants. So that's the weird thing about modeling, is that, very often people's criticisms, especially when they come from outside, are, oh, that model leaves this out or leaves that out. It's not realistic enough. But it turns out if you add too much realism to a model, you can end up actually taking all of its ability to answer those what-if questions away. It ceases to be useful. So that's our goal won't be to build the most accurate models. It'll be to build the most useful models. To do that, we're going to borrow tools from mathematics, from statistics, from programming. So the big point here is that this course is not just a programming course. It is largely a course that takes all of these things and integrates from your past courses in order to try to build these models that have useful insights, but also are executable on machines in a relatively short period of time. So you can imagine if you built, people talk about, computer graphics for movies and how it might take them 3 years to animate a movie. But we don't need 3 years to animate a model of a factory floor. Is not going to be a useful model. So how do we get the most insights out of a factory floor simulation that could actually simulate in a week or an hour? And what do we lose by going from a week to an hour? What do we gain by going from an hour to a week? Those are sorts of things that we'll also talk about as we get towards the end of the course. So good statistical methods are going to be involved in sort of a lot of these things. The basic outline of what you'll see is before the midterm, we do a lot of probabilistic models. After the midterm, we switched a lot of statistical methods. And during the lab and a little bit during the lectures, you'll see introductions to the actual software that will be used to bring all these together that you'll actually use to then work on your final projects. And all that's crammed into this one course, but if you really are interested in this stuff, then there are certainly more advanced courses which just sit firmly within each one of these bubbles. So a lot of those will have our grad students do. So that's kind of the recap of what I wanted you to take from Tuesday's lecture. Are there any questions about any of that, or about course policy, or anything moving forward? Is there anything in Canvas that I've forgotten to publish and don't realize it, or anything like that? All right, if you do notice anything, so you think something in Canvas should be released, and when you click on it, it says it's still waiting or whatever, just send me a note. It is possible. And again, I did a lot of revamping of the course from last semester to this semester, and that required moving some things around, and so there may be some things I didn't catch. And that's the reason also why I'm still working on Unit C, and that's why it hasn't been released yet. All right, so today, we're focusing on simulation. And so there really are these 3 major simulation methodologies: agent-based modeling, system dynamics modeling, and discrete event system simulation. Now, system dynamics modeling is the main focus of IEE477, which is a course which a lot of the engineering management majors take. So it is kind of a nice companion simulation course, semester long. They use a tool called AnyLogic, which also can do DES modeling. So it's something that if you're interested in and you've got the credits left over, you might be interested in that class too. It's very different the way they simulate, but it's complementary to what we do here in this class. So this class is these discrete event system simulation models. So I'll get into those things in a second. So the system dynamics modeling they go over in 477. So this is basically a graphical way to build differential equations that represent the average behavior of systems over time. So this isn't like, this is stuff that you're not gonna, I'm not gonna, on the midterm, I'm not gonna ask you that much about system dynamics models or anything like that, because again, that's the focus of a different class, but I'm just providing it here as a contrast to what we do. So rather than modeling individuals, so like the types of models that we model in this class, every individual might actually be represented by some entity in your model. And here, you represent groups of individuals as basically stalks of fluid that fill up little bins or leak out from little bins. And so these are called stocks and flows. And so you can imagine, you could say, well, I'm going to model the number of people interested in Dr. Pavlic's lecture right now and the number of people waiting for the lecture to end. And so you can imagine that maybe this starts pretty full, but over time you start trading liquid and it starts going into this bin here, and then they go the other way. And then hopefully the class ends, and then you're refreshed, and then maybe the next time you come in, hopefully this fills back up again. So, so that is modeling everything as these smooth dynamics over time. And they roughly, rather than capturing a realistic kind of stochastic trajectory that you might get out of a real, say, classroom, it models kind of the average classroom. On average, this is how many people are listening in right now and how many people have checked out. And over time, how do the averages change over time? So that's what system dynamics modeling are. The advantage of this is it can be very fast to simulate and requires relatively few parameters. It's like, it's basically a graphical representation of a simplistic mathematical model. A disadvantage is it often doesn't capture those second-by-second nuances that other simulation models can, because it's only modeling average behavior. The very stark alternative, so here's like an example of that. So this is for an airport, and so you can try to mind map and come up with all the possible things that you think might be important when thinking about airport operations. And you can say, well, what are causes for airport delays? And then you can imagine a little refueling, where does that fit into there? Military flights, increased technical, there's all these different things that this came from a paper that I just borrowed. And once they kind of, shotgun them onto the map here, then they drew causal arrows to sort of say, this thing has a causal effect on this thing has a causal effect on that, and they kind of started looking for loops. And from there, there's a way to turn a diagram like that into a diagram like this, where you've got those stocks that I talked about and those flows. And it turns out that behind the scenes, this ends up being equivalent to a differential equation model like you might learn in sort of your first class after the basic calculus classes. So, a nice ordinary differential equation course where you end up being able to solve, like this is like x dot is effectively this line and box together is basically x dot equals, and this is a y dot equals, and when you end up solving this thing, you end up getting a trajectory about x and y over time. And so that's what so this ends up being is that you're able to sort of plot these trajectories, and they're effectively the average behavior of, in this case, an airport system, and they've tried them for different parameter choices and saw how these trajectories over time changed. And so you can see that, well, if I make these changes in parameters, I get these changes in the average behavior and so on. So that's how a system dynamics model sort of is approached. On the total flip side of that is agent-based modeling, which I'll give you a little bit of an introduction into in Lab 4 with NetLogo, another program that is commonly used for agent-based modeling. And here you actually model every single individual, and even you model the space around them. So not only would, if we were doing an agent-based model of this class, every one of us would show up in that model, and the chairs would actually show up like agents in the model. Every little square of carpet would show up as an agent in the model. And you set up rules for how those agents interact with each other and with the chairs and with the carpet. And so whenever an agent bumps into another agent, it then triggers a rule that says, all right, you just bumped into another agent, what do you want to do? And you can say, all right, well, I'm going to change my mood to angry, or I'm going to transfer money to that other agent, or something along those lines. You come up with these rules, and you just simulate all of these interactions among these agents. So it's great when you can understand how small-scale microscopic agents interact with each other, but you don't quite know what happens when you put 100 of them in a room together. So it's good for looking for the emergent properties that come out of understanding the local interactions, but not understanding what the kind of global phenomena might look like. So the advantages is it's potentially very realistic because you can actually simulate, down to microscopic detail a lot of what's going on. Disadvantages is it can be very slow to simulate because you have to keep track of a whole lot of those different individuals. And the models can be as difficult to understand as the real systems themselves because they do show this emergent behavior, and sometimes it's not clear where these patterns came from. So, and it's a large number of parameters, which maybe make them also difficult to set correctly. And so I've got kind of, I think, a video of that. So here's an agent-based model of an airport, specifically, which I'll animate here in a second. These are passengers moving through a model of different security lanes. The green ones are open, the red ones are closed. And so the person who's made this, I took this out of an academic paper, the person who wrote this model gave different rules for these passengers as they move around. And you'll see they basically are just going to move around randomly in this area here. They're going to hit these lanes, and if they hit a green lane, they'll move down it. If they hit a red lane, then they just kind of bounce off of it, and then eventually they can exit and go to the gates. And so if you animate that, looks something like this. Now, on one hand, doesn't look very realistic because this is not how you queue up in an airport, right? And this is, and on the other hand, there's some aspects of this that are kind of interesting. The way in which they move through here, and I could go through and change, which queues are open and which queues are closed, and I can actually measure how many passengers are getting through, how many passengers are tied up in the metal detector. Yeah, question?
Would this model work for networks?
For networks?
Uh-huh.
What type of networks?
Just like networks in general.
I mean, absolutely. There are tons of agent-based models about networks where you can definitely can build, agents that are interacting, but they're forced to interact with only a few others, and you can model that as a network. There are networking elements. You can actually model a link between someone as a type of agent, and the networks are definitely something that fits within this formula. But so you can experiment with this model, and it has a lot of interesting, rich dynamics. The real question is, does it tell you anything useful about airports? So, and that's not clear to me. But where these typically become useful is to test so-called null models of system behavior. So if you do notice a pattern at an airport, and you might be like, oh, that's a weird pattern. I wonder if that's for this really complicated reason or this really complicated reason. Someone might come up and say, actually, that's exactly what you'd expect just by people walking around in a confined space that only have a small exit to get out of. There's going to naturally be this pattern or something like that. So that's kind of a null model. It's a simplistic explanation for a phenomenon you get. And if you could say, okay, well, if that's the case, I should be able to build a cartoon airport that basically the only thing that it'll have in common with a real airport is this spatial component that we think is the null model. And when I simulate this thing, then it should also show the same pattern I see in a real airport. If it does, then it gives me confidence that maybe the pattern I see in a real airport isn't for any complicated reason, it's just for these spatial constraints or something like that. So there's certainly other more advanced and more interesting things you can do with agent-based models, but you just have to be careful about them because it's really hard to justify that your agent-based model is actually simulating your real system unless you go to a whole lot of effort to like get a whole map of like Phoenix Sky Harbor and have your agents move through them and have your agents move through in exactly the way people move through and all that. Because there's so much detail you have to get right. And that can be a real burden on the model. And then there's what we'll be doing, discrete event system simulation. And so in here, we're also modeling individuals, very similar to agent-based modeling. But our individuals are like these passive marbles that arrive and are shuttled through the system by processes that are like vacuum cleaners, sucking them up and shooting them out. And we don't model what the agents do, what the little marbles do when they interact with each other. We model what those vacuum cleaners do whenever a marble bumps into them. And so that's why we often see them depicted this way, where you've got these different blocks, where all the action is really going on in the blocks, and they're pulling these marbles in and pushing them out. And so the thing here is that these agents, the big focus on this modeling is agents that are competing for limited resources. So, if I was not me, but if I was someone that would, that there would be, 300 students waiting to come in my class, and it was always first come, first served, then these chairs would be a limited resource. And so people would flood in and they'd try to find the chairs, and if there were no chairs available, there'd just be a line of students in the hall, and maybe they'd have to leave or something like that. And so that could easily be modeled in this sort of framework. So where you've got limited resources that entities hold on to for a short amount of time, and while those resources are held on to, all the other entities just have to wait for those resources to become available. And I'll show examples of that. So the key modeling parameters here are how the individuals show up at the system and how long each of these limited resources spends with an individual that gets access to that resource. Those are the two things that we will spend a lot of time modeling. And once we model those, then we hit go on the simulation and see how well it works. The advantage here is it's much more realistic than system dynamics modeling like you see in 477, and yet it's not quite as detailed and doesn't require as much computational time to simulate as agent-based modeling. So it's a good fit to many of our engineered systems too, because we often engineer a whole process. So unlike the free-for-all that was sort of simulated in the agent-based model, we often know that part A arrives at station 1, and then it goes to station 2, and then it goes to station 3, and we've sort of engineered a process. So we kind of know a finite sequence of events that these different entities can go through, and that is works very well for modeling here. Disadvantages are is if you do have some weird state-of-the-art system where you kind of allow things to self-organize, then an agent-based modeling approach might be, if you're doing some weird nanoscale manufacturing thing where you just dump a bunch of nanorobots into a big pool of resources and let them do what they do, then in those cases, it might be hard for us to know the exact sequence of events that will go on under the microscope. And so an agent-based model might be a better tool to understand all the things that could happen. But in a standard manufacturing system, these work pretty well. And the other downside here is we'll see that this is going to require a little bit more mathematics, a little bit more statistics than somebody programming your average agent-based model. All right, so this is what a very simple discrete event system simulation model would look like in Arena. This is, again, keeping with the airport here. Passengers arrive, they get checked for proper identification, and then they either, if their identification looks good, get cleared for the next step, which we're not modeling, or they get denied, and they have to go back and get new ID, which we're also not modeling that process. So this is how you start. You draw the process out. Then you also can actually draw in these graphical depictions of here is the document checker, and here is the line of people waiting to get their documents being checked. And you can throw on these graphs, so as the simulation's running, it can show you the width, for example. So it can show you how many passengers are actually in the system, either waiting or getting checked, somewhere in the system here. And then this ends up being a very big deal to our clients. You can actually take this 2D representation and turn it into a 3D representation like you'll start seeing animated here. So I'm running this simulation now, and so you can see this 2D representation, the document checker, it'll check someone's ID, the others are waiting back here, and Arena can then also render that down here in 3D. Now it's identical to the 2D up here, but it's just wrapped around a 3D skin. And so there's nothing really special here, but for whatever reason, the people we work with love this stuff. And so, I mean, I'm often asked, I was just asked 2 days ago, do we have a license for Simio, which is another one of these languages here? And I said, oh, no, sorry, we only have a license for Arena, but you know, all these things are relatively similar. Do you have students that are working on a project? And the faculty responses said no, but the sponsor really likes the 3D images, and we have a bunch of Simio models that we thought we could animate for them. So the sponsor really likes seeing this stuff. It's identical to what's going on here, but it's in 3D. Now, the other important thing here, if you compare this to agent-based modeling, is that you know, all we're really modeling is this process here. But now that we've visualized it, it shows plausibly how individuals might line up in space. We haven't actually modeled the effect of space. Agents aren't interacting with space. They're just waiting in line and interacting with an agent up there. But we can now show how they might interact in space and how that would properly be captured by our model. And so that adds a bit of, argumentative strength to using these models when you can show people these visualizations. So yeah, they're not spatially explicit, but the visualization makes them look plausible. And I think that even goes more for this hospital example. So here's another example where I haven't shown you the models yet, but this is the 2D visualization of them arriving at a drop-off, going to a receptionist, waiting in a waiting room, getting assigned to an internal waiting room, getting assigned to beds. The beds are either occupied or not. The patients might be critical or not. And so this, I argue, is modeled by these very simple maps of blocks. But visualizing in this way makes it look almost as realistic as an agent-based model, if not more so, because these agents aren't just wandering around randomly. So this ends up being a very powerful tool for communicating your model to a sponsor or a stakeholder. And I can keep track of stats right alongside here, as if I'm, you know, have a God's eye view of a real hospital. And then with those, I can even aggregate those stats. And these are right inside Arena. It can give you these all these different data that come right out of that model. And inside, what's actually driving this is just a relatively simple set of flowcharts that look just like this. So really all the work went into drawing these flowcharts. And then there's a little bit of work in making the graphical front end, but it just connects to this. So the real sim work is just done in parameterizing how long do they wait for the triage? You know, how often do they get secured into a room, and so on and so forth. And once you have all of that, then it's easy to visualize here. So most of the effort goes into this stuff, and then this just sort of comes out for free. And then, you know, for the airport example, so again, I've just taken that small example, I've added a bunch more steps to the process after they go through ID check, and it's, again, a relatively simple model, but you end up getting stats that come out of it where I've got, you know, real variation here in passengers. How long do they wait before checking their ID is checked? When they finally go through to the x-ray, the baggage check, how long do they wait? And notice there's confidence intervals here. And so it's not just an average. It actually shows me a range of times with maxes and mins that they can be waiting. So it really does start looking like a real system that we can do real experiments with. And we have a wide variety of performance metrics that we can apply to that system. I just showed you waiting times. I can also show you utilization. I can show you number of resources that got seized over a particular time period. And I can even have it automatically accumulate costs. I know that I have to pay the agents so much per hour. I know there might be a certain amount of cost for the machines to run. So as I flip on new machines, as I acquire new agents, it can automatically keep track of the bookkeeping for me and then just give me a nice report to tell me how much these particular performance values cost me in terms of real costs? All that can be done right inside the simulation model. It's not just for airports, it can also be for, warehouses. So this is another example from a 3D, actually this is Arena 3D again. And then there's even these cases, so this was a paper that came out not that long ago, 2016, where it was highlighting the use of Arena to improve the operations of a food bank. And so they used Arena to adjust, so here's the Arena model, they used Arena to adjust how they managed their volunteers in the way in which they went out to these farmers who had these extra apples to pick. And so they wanted to maximize the yield from this, and they optimized their operations through a simulation model and greatly increased the number of apples that they were able to gather for this food bank. And so that's an example of the other sorts of things that you can do in Arena. So it's very widely applicable, and it's relatively powerful and not that complicated to use once you learn a little bit of math and a little bit of stats. Are there any questions about trying to understand roughly what simulation's for and where we're going in the class? Anything that's come up here? Yeah.
Can you explain more how the chart works?
Oh, the chart. Oh, yeah. So that's this was sort of just meant to be a survey, and I'll get into a little bit of that here in a couple more slides. But that's going to be kind of the focus of this class, is getting to the point where you'll be able to draw those. I'm not expecting to come out of this class, this particular lecture, and start drawing these things. That's kind of what you do after you come out of this whole course. All right. So I'm going to skip an attendance exercise for now and just go on to the modeling. So I'll have more of those attendance exercises later. Don't leave yet. But so let's make sure that you're equipped with the terms that you need for the first lab, which you saw yesterday, and many of you have already turned in, and the first homework. So in these simulations, in order for us to talk about them, we have a couple of different terms. And so I've used this term system a lot. So a system, roughly speaking, is a group of objects connected by some joint purpose. We're very interested in the boundary of the system. So I've already talked about a couple of different systems I've shown modeled here, where the modeler has left out particular things that were not of interest to the question they had in mind. I'm only interested in the document checker, so I'm not going to model the X-ray machine. So that's what I mean by choosing a boundary of a system of interest. You can always expand that boundary to make your system more realistic, but if it doesn't help you answer the research question you have in mind, then maybe you're going to add a bunch of stuff that might be actually getting in the way. So having small systems is not necessarily a bad thing. So again, you're not shooting for realism, you're shooting for utility, insightfulness. So examples for contrast, 100 students in a classroom. This classroom could be a system that I'm modeling where maybe I'm the limited resource and you're the entities waiting on me, or 100,000 students on a campus, maybe when there's no classes. So maybe at that point, we're not actually modeling anything to do with the instructors, but we're modeling how the students make use of the spatial resources. So a very different scale. Both models involve students, but you're modeling very different things. And because you're modeling very different things, then within the model, you're not just simply taking this model and adding to it. You're building a totally different model for that one. A dynamical system is a system that changes over time. In your, say, deterministic OR courses, where you're modeling, say, where to put gas stations in a city, we're not interested in the dynamics. That's a static problem. I know basically where the cars are. I know basically where people live. And I know I only can put 4 gas stations around. So where do I put them? And so I put them in these places, then I'm done. Dynamical systems, I actually do care about how things change over time. I do care about not just how many passengers get pushed through the airport at the end of the day, but I care about in the middle of the day, how long did the longest waiting time, how long was the longest waiting time? So how long did I make some poor person wait during the middle of the day? I care about the entire day and how things change over time. So that's what we mean by a dynamical system. Because we have dynamical systems, we have to use this word state. And the state of a system is just the current value of a system, and that's the thing that changes over time. The number of students in a classroom changes. The number of passengers waiting at an airport changes. And so the state of the system is the current number. Now we store all of those states in state variables. And so this is something that students often get confused about, the difference between state variable and state. State variable is just a variable. It's like X or passengers. It is the thing that we use for the bookkeeping. And so we might say passengers equals 5, which means that right now there are 5 passengers waiting. But it might be passengers equals 7 in a couple of seconds. Passengers is the state variable, and 5 is the state. So don't refer to a variable as a state, because those are sort of different categories entirely. Now, we referred in this class to discrete and continuous state variables. Sometimes you also heard these as discrete time or continuous time. And in this class, a discrete state variable is one that can assume any value, but only jumps at countable instants of time. So if I were to draw a timeline, and if I were to maybe put on the y-axis here my state variable x, a continuous variable, a continuous x, might smoothly change over time, but a discrete state variable will hold a particular value, and then it'll jump to some other value, and it'll jump to another value, and it has all of these jumps. And these, in instance where the state variable, or where the state jumps, we call them events. And mathematically, we say that there is a countably infinite or finite number of them, and that's what makes it discrete. So that's here, things are smoothly changing over all time. Here, they're only changing countable instants. I can count the first change, the second change, the third change, the fourth change. That's what we mean by discrete. So we study discrete event systems. So all the systems that we study will have these types of transitions in their trajectories. We can add in more advanced work, systems that also do this. But in this class, we're focusing just on systems that have these jumps. So it turns out there's a lot of them. Most of the systems that you worry about as industrial engineers, as operations researchers, fit into this discrete category. So yeah, 475, that's what we focus on here. Are there any questions about that? Systems, discrete, you know, to check to see if there's any, yeah.
Question about the state variable. Can we define a state variable for different components like entity, resources, for example, a number of resources available, number of incoming students, number of event activities? Can we define this?
Right.
Are
So
we calling this a state variable?
yes. So any sort of thing that I use for bookkeeping. So within one simulation model, I might have the number of students, the number of instructors, the number of machines that are busy, the number of machines that are idle. Anything that is a snapshot of the current world, anything that helps capture that is what I'm calling a state variable. And then the values that those state variables take, I'm calling collectively together the state of the system. So, so a particular, like I said, you know, if the state of the system might be the number of students in the classroom and the number of instructors busy teaching. And those are, I would say, 2 state variables, but I might still say the state of the system are both of those things together. There are 30 students in the classroom and 1 instructor that's busy teaching. Yeah, question?
Can they be also resources?
Absolutely. State variables can keep track of resources too. Like in that instructor case, if I'm a resource and you're entities, which we're about to get to here, the number of resources busy is a common state variable. So yes, it's a snapshot. It's like if you were to erase all of history, and then it's everything you would need in order to move forward without looking back on the history. So it gives us all the information we need for the simulation to move forward. It's the state of the system. All right, so then we also have resources. This term's come up. These are components in limited quantity that are needed for performing these activities that we're interested in. And so an activity might be teaching the class. An activity might be checking an ID. An activity might be scanning a bag. So these are activities, are these things that I'll define better here in a second, but that they are, you kind of roughly know how long they're going to take before even knowing anything about the state of the system. We just know that statistically, classes take roughly 75 minutes. Statistically, it takes roughly a minute for a bag to get through an X-ray machine. That's what makes them activities. We can say ahead of time, we know roughly how long they're going to take. But in order to perform them, you need resources, and there's only going to be a limited number of them, and that's what's going to cause people to wait on those resources. So I gave these examples already, X-ray scanners, TSA, etc. Entities are the things that wait on the resources. So entities come and go where resources generally are always there. You certainly can take a resource away in the middle of a simulation. You can make an X-ray scanner break down. You can tell if you've got 3 cashiers at a restaurant, you can tell some of them that it's okay to leave, and you can go down to 1 cashier. So resources can leave, but they aren't sort of our major focus. They leave, but they just kind of change the structure of the system when they leave. The actual system, but anything that is involved in the structure of the system is a resource, but the things that are using the system, that are just passing through, are the entities, and they're the things that are made to wait. So, and that wait is something that we refer to as a delay. When you're waiting on something, not because you knew ahead of time it was going to take you roughly this amount of time, but due to some state of the system, then that's a delay. As an example, when you go to get your bag scanned, once you get to the X-ray scanner, there's a sigh of relief because you know roughly how long it's going to take for you to finally go and get to your gate. But when you're standing in line for the X-ray scanner, you have no idea how long it's going to take for you to actually get to the scanner. So the time to get to the scanner where you're waiting on everyone else's activity is a delay. But when you actually get to the resource and hand your bag off to the resource, then that is when you've entered an activity. And those two things matter because we model activities, but we don't model delays. Delays come out of the simulation. Attributes. We can differentiate entities by their attributes. We can say this person is a different age, this person arrived at a different time, this person has a different need. This person came in because they had a cold. This other person came in because they're gushing blood. So they can have, we differentiate, and we might run entities down different paths based on their different attributes. So I give other examples here, whether they're got pre-check status, when they arrive at the airport, the number of times they've been rechecked through security. And then this activity versus delay distinction. This is something that will come up again next unit, next week. So don't worry too much if you don't see it here, but I'm highlighting it here so as you move through the labs, as you move through the homeworks, you start looking for it more. Because this is going to be key, is that we model activities, we measure delays. Delays come out of the simulation, activities go into the simulation. So activities we know ahead of time, delays we run the simulation to find out. All right. So quick examples, manufacturing systems. The entities might be the parts that go through the manufacturing systems. Things that differentiate the parts, different features, different numbers, colors when they arrive. Those parts don't just sit there, they wait on resources. There are machines that process the parts. If that machine's busy, the part's got to wait. It can't get into the machine. Question?
I have a question actually about the last slide. So
Yeah.
when something happens that's considered a delay, like at the moment that it occurs, is that an event?
So an event, it turns out that activities are always bookmarked by events. And that means that delays are also going to be bookmarked by events. But during the delay, like while you're waiting, there may or may not be events going on. But events always happen at the end of the operations. So you can think of the start of an activity or the end of an activity generates an event. But the generation of event may kill a delay. So you're in front of me in the security line. I'm waiting on your bag to go through. Once your bag goes through, that was your activity, which will generate an event once it's through the machine, which means now the machine's idle. And now that the machine's idle, that kills my delay because my delay was your activity. And so me waiting to get the opportunity to put my bag in was a delay on me. And I couldn't have known ahead of time because I had no idea how many people were lined up ahead of me. But now that I can step up to the machine, now I know it's going to take 30 seconds to get my bag through. Does that help?
Okay, well, if the machine broke down,
Yes.
would that be an event?
Absolutely. If the machine breaks down, that's an event. It changes the state of the system. We had 4 operational machines, now we have 3. And then as a consequence, now there aren't as many machines available to run these activities. So we're going to see a lot more delays because they'll be arriving at the same rate, but they won't be clearing at the same rate. All this will become more clear as you guys start building this stuff too. So yeah, activities and delays. A delay, the time the part waits in line until the machine is ready. State variables, so we could have a variable representing for each machine whether they're busy or idle. So together, if I have 5 machines, I might have these 5 state variables, or a state vector, if you like, and those together encode the state of the system, where the current state of the system says there's 3 machines that are busy and 2 that are idle. So we might ask, why are some machines idle? Why aren't they always busy? And that goes back to these delays. So the same way that entities can be delayed, yeah, question?
Are the systems we're looking at in this class, are they always binary,
Oh, no, state variables don't have to be binary. So state variables, and they don't even have to be countable. A state variable could be the temperature in this room. Even if they aren't binary, but they say they are countable, the number of students in this room, that could potentially be infinite if it's a big enough room. So they're very often counts, these state variables, in a lot of our systems, but they don't have to be. So they could be, I'm allowing the value space to be as smooth as you like it, but time is the thing that I'm kind of cutting up into these countable chunks. Although most of the systems we'll look at, the value space will be countable as well. Does that make sense? Okay. So machines can be idle because they're waiting for other machines to finish, and there are no entities ready for those machines yet. So if you have, this person here is going to be idle if no parts have come through there because maybe they're all tied up in this machine here. So we will periodically, even though you have a bunch of machines, a bunch of them could be idle, and an important performance variable will be keeping track of how much idle time we have.
So are delays basically like a change in your expected exit rate when you run the simulation?
Delays will cause a change in how often. If you have a lot of delays, then most likely your entities are going to be slowed down inside the system and thus not exiting as quickly as they could. So, or put another way, when we do operations research with simulation, we're often focused on minimizing delay. And by minimizing delay, we maximize output throughput. Does that make sense? Question? No, go ahead.
To clarify, so an example of a state variable would be that machine 1 is idle.
Exactly.
Okay.
Yeah, the state variable would be the machine 1, and then the idle or busy would be 2 different states.
Okay.
Question?
So at like a TSA security line,
Yes.
let's say the security people, would they be an entity or a resource? Like let's say they have different shifts or something, so that maybe they move in and out, but then they're also kind of like a resource. So
Excellent question. And that depends on what research question you're kind of asking. So most of the time, the TSA agents will be resources whose resource availability might happen to change over time. So most of the time, we're focused on the passenger experience. So we're keeping track of passengers that come in and go out. Now, let's say that the airport hires you to optimize, I don't know, the lunch line or something like that. And so for these TSA agents, maybe they have a special TSA cafeteria or something, I don't know. But in those cases, then you might shift your focus in thinking about agents that arrive and depart. There might even be a way for you to build a model of operations where both the agents and the passengers are entities that arrive and depart. But it gets a little contrived in that case, but I can't say it wouldn't happen. But the time when it would happen is if most of the time people ask, like, what are the stats on how long our passengers wait? But if for some reason you wanted to keep track of per individual TSA agent, like how long does this TSA agent stay on their feet before they get a different job that allows them to sit down? Well, in those types of human factors things, even though the TSA agent will play the role of a resource, we might model them as an entity because we might want to keep track of, when the TSA agent arrives at a particular job, when they leave a job, when do they get fatigued. So this will become more clear as we move on, but there can be ways to turn resources into entities. But most of the time, the thing that is the most limiting factor is going to be the resource, and the thing that's sort of available in infinite quantities is going to be the entity. I think I saw another question up here, yeah?
Sometimes the activity itself takes longer time than usual.
Yes.
So is that considered as a delay?
No, that's an excellent question. So I define activities as something we kind of know ahead of time, but we know their distribution ahead of time. So we know on average it takes, and that's what we'll end up seeing in this class, is that we're end up going to find out how to put those distributions in. If you know the distribution ahead of time, it's an activity. If you don't even know statistically how long things might take, or if your stats depend on, like if you could say, well, how long will it take to wait in the security line? And you can say, well, if there are 10 people ahead of you, it's going to take 15 minutes. If there are 5 people ahead of you, it's going to take 2 minutes. Well, that when there are tells me that you're modeling a delay and not an activity. So if you've added conditions, if somebody asks you a question that you have to condition on the state of the system in your answer, then you've described a delay. If somebody asks you a question, you can just spit out an answer and it applies for all systems or all states, then you've identified an activity. Does that make sense? Question?
What's the difference between resources and state variables?
So resources are the things themselves. I am a resource. But a state variable is a mathematical variable used to represent me. So whether I'm busy, so my name is Ted, so if I created a variable called T, and T was either 0 or 1, then the resource that we're modeling in reality is me, but the variable that we're using to represent whether I'm busy or idle is T. So, and there could be multiple state variables per resource or something like that. So it's more of like resources are out in the real world. Like it's kind of like you go to your stakeholder and you ask them what the resources are. And then you go back into your room with all your other fellow engineers with your whiteboards, and then you come up with the state variables. And the state variables are what's actually used in the simulation to do the work. But what you're representing is the resource out in the real world. Any other questions from here or virtually? Yeah.
For the lab, I think you talked about how we had to do state variables. Is there a big difference between doing the state or the state variables?
Yeah, you have to, if I ask you for a state variable, I want you to say like number of, machines busy. If I ask you for a state, then you could say the machine is either busy or idle, and you would sort of circle like the busy or the idle part. I thought I saw a hand up here. Well, let's move on. I think some of these questions will get answered as we move forward here. Here's another example, a university. I'll go through this just kind of quick here. Students, I'm modeling as the entity. They are differentiated by GPA, major, their names, their ID numbers, etc. By the way, never put your ASU ID number on an assignment that you turn in. I don't need it. No instructor needs it. If they ask for it, they're just being jerks. And it jeopardizes your privacy. The most an instructor should ever ask for you is for the last 4 or 5 digits, because that's enough to differentiate. But in the end, your ASU Right ID, like your login name, is fine. So I noticed in some of the homeworks going in, people are putting their ID numbers, but it's like that puts now if somebody happened to get those assignments, then they have your ID number and they can do apparently bad things with your ID number. Whatever people do with Social Security numbers, picture that. So So I never need that, so don't give it to me. I might ask you the last 4 or 5, especially on midterms, but that's just to make sure we're keeping that unique. Resources, classrooms and instructors. They're limited in their parts of the systems, whereas the students are moving through the system. Activities, the duration of class is an activity, whereas delays, the time you wait before you can actually enter the class. Even though the class is scheduled for 10:30, the last class might linger a little bit of time, and you have to wait for the classroom to become idle before you can come in. And that amount of time that you're waiting for them to finish their activity is your delay. Events, students arrive, class begins, class ends, or a fire alarm, that's an event. All these things change the state of the system. State variables, so down this column, a classroom, instructor, and number of students are all examples of state variables. Down this column are the different states that those state variables can take on. A classroom is either busy or idle. An instructor is either lecturing or proctoring, or maybe other things. A number of students might range from 0 to 104. So, each of these particular instantiations is a state, whereas these 3 things are all state variables. All right. Any other questions? Again, let's move on because I think that some of this will get answered. So we combine all that stuff together, and eventually you'll draw these diagrams. I've already got these questions about what do these diagrams mean. This is the rough kind of mile-high view of what these flowchart-like diagrams are. Most of this discrete event system literature borrows from kind of flowcharting to draw these things. They all use symbols that look a little bit like this. This one here basically is the thing that creates the entities. It manages the number of entities that are generated on an arrival event and how spaced in time those arrival events are. So how often do they arrive and how many arrive, all pop out of here. We also have these rectangular blocks, which are where the activities are stored. They process those entities. So that's where, whereas here we say, what is the distribution of, how many arrive and how often they arrive. Here we model, given that an entity has arrived here, how long is it going to take while it's here? What are you going to do to that entity while it's here? Are you going to change its attribute? Are you going to duplicate it? Are you going to remove it? So this is where a lot of the action happens in the logic that's specific to your system, is coding these things up. Then those entities can go to these diamond-shaped things, which look like, like if statements in a flowchart. So entities arrive in one corner and then they exit the other corners. And this allows you to say, oh, this entity has it's got priority as an attribute, indicating that it has priority. So I'm going to send it through the priority process, whereas all the other ones go through here. Here's the pre-check route, and here's the everybody else route. This entity is actually part of the crew, and so they go out this other route here. And then finally, there's an entity, it's something that disposes of the entities, and that's where all the entities go to disappear. That's the field that they all are taken to at the end of their lives. And so that actually gets rid of the entities. That ends up being important for your student simulations because the student version of Arena limits you to 150 entities. So when you're done with them, you don't just keep them around, you pass them to a dispose, and that allows you to free up more entities that you can generate later without running into that limit. So these two are the things that generate events. So the entity creation time here and the process time. Things like machine failures, you can also put inside here. It'll take resources on and offline. So that's where most of our modeling effort goes into, is to build these things here. And that's what really changes the state of the system. And an example of that, we've already seen this one here. So passengers arrive at security. If I were to drill down into this block, I could say how many passengers arrived and how frequently they arrive. And there are statistical distributions instead there that I can put in. Check for proper identification. If I were to drill down into this rectangular block, I can tell you how long does it take to check for an ID. What's the minimum time? What's the maximum time? What's the average? What's the distribution shape like? All that I can put in through here. Inside this block, I can say, well, based on the properties of the entities passing through, do they pass security or fail? Or I can even just have it flip a coin and say, well, 75% of them pass and 25% of them fail. And then here, this just gets rid of them. It might take stats on how many got cleared and how many were denied, but then that's basically it. So the stream of passenger arrivals is modeled there, the time the agent takes there. The delay comes into play that Arena knows that there's a limited resource in here, so it will automatically build a queue for you. And if entities try to enter this block, when this block is busy, it will queue them up between these two. So you actually would just see them wait. And then once the resource is available, the one in the head or however you design your queue will then go into the block. And then these, again, cleared and continue, they make the entities disappear. So events here are the arrival events. Here are the beginning and ending of service events. And then the entities are our passengers, the resources are the agents, and the activities are the time each agent needs to check each ID. Delays are how long they wait. All right, so any questions about this kind of graphical depiction? All right, so let's then cover the last bit of this. Why is this a stochastic simulation course? You know, what do we mean by stochastic? That's the last term we have to define here. So I have this simple model of someone coming up to an agent to have their ID checked at an airport. And I would really like to capture the real variation between passengers arriving. I would really like to capture the real variation in how long it takes to check an ID. And I really would like to capture the real variation in how many actually arrive at the airport with ID that cannot be cleared. I want to capture real variations because I want this to be a stand-in for a real system. The question is, how do I do that? So if I just zoom in on just this variation, how do we model the time between arrivals? We can imagine at least 3 different ways we could do that. So let's imagine the real timeline is something like this. Here's an hour, and this orange passenger is going to go into an orange plane. They arrive, roughly a decent amount of time ahead of time for one passenger, probably enough time to get through. Here is a family that arrives. They've recently had a child. They're not really used to having children yet. So because it's taken them so long in just getting this child together, they arrive really late and barely make it onto their flight. Now another family has 2 kids. They're well practiced, so they know what's going on. So they arrive way early and have plenty of time to get through. Now, somebody else just is, they just are always late, and so they're also probably barely going to make it through. But then I might also have somebody arriving for a different flight. And now, when I'm actually modeling the airport and taking stats on the airport before building my simulation model, all of these passengers just look like passengers to me. And so if I'm looking at the time between arrivals, somehow I have to take into account that there's multiple flights, there's individual differences between these. I mean, it's a mess. So I could say, well, what's the average time that between arrivals? But I see that there's some that are going to be less than average, and some that will be more than average. Now, the deterministic approach would be to just assume that there's always the average time between arrivals, and I could use something like you see in, say, 470. Where you kind of just assume, a rough arrival rate. And I'm being a little facetious. 470 is not quite this crude, but you could still imagine building, or 477, you could imagine building a dynamical model, a very simple mathematical model based on the idea that every passenger takes exactly 20 minutes in between them and the previous passenger. But that doesn't seem very realistic. That is one deterministic approach, where I just say it's always there. The other deterministic approach I could do is I could try to come up with a mathematical rule that captures all of this realistic variation in one. So it says, all right, based on their family size, their occupation, their distance from home, their flight number, all of these other things, I could just come up with a way to predict exactly what each one of these times will be, and hopefully get it right. But you can imagine it would be very difficult to come up with a deterministic rule that captures all the nuances of every single person that would arrive at an airport. It's impossible. Well, I mean, it's something that I guess might be possible, but it is totally impractical. Nobody's ever going to be able to do that. But the thing is, when I stare at this long enough, I start wondering, what if I just rolled some die? And I said, well, if I get a certain number on the face of a die, then I'm going to give them a certain time, and another number, I'll give them another time. Well, then I start getting a random allocation of times here. And the question is, does this outcome look that much different than the real outcome? And if it doesn't, then all I need to do is find the right die, and I actually end up generating pretty good inter-arrival times that generate trajectories that look just like a real trajectory. So that's what we do in stochastic modeling. We build models that use randomness instead of deterministic rules. In fact, the word stochastic comes from the Greek for guessing or conjecture. A lot of people think that stochastic is just some synonym that we use for random, and we're just sadistic, and we have two words for random or something like that. Random means something probabilistic, but stochastic is describing a way in which we model where we use randomness even if we know that the underlying processes aren't necessarily random. We don't care if the underlying processes are random or not. We just make a guess, a conjecture, that they're random because it's easier that way. And once we do that, it reduces our modeling burden because now we choose one or two parameters of a random distribution, of a probabilistic distribution, and we get variation that looks just like real variation. Compare that to that deterministic rule where we had like 15 parameters, we probably still would be wrong. So that's the beauty of stochastic modeling, is that we are substituting randomness for all these degrees of freedom that would be really difficult to pin down otherwise. And so are there questions about that? What I mean by degrees of freedom or using randomness. So when we talk about stochastic models, we're saying that we have a model that assumes randomness even though we are very positive that the randomness is probably not actually there. Skip this attendance question too. So how do we implement these models? This is what goes on behind the scenes. This is stuff that you'll see down in lecture E1 and E2, but I just want, as you start doing hand simulations, you to see where those numbers are coming from. If you had a 20-sided die that you rolled, you could basically come up with a rule where you could say that, well, if I roll a 1 through a 10, I get a very long delay. Otherwise, if I get any of these other pairs, I get maybe long delays, short delays, average delays, very short delays. And so as I roll that die, I've biased this die to give me very long delays very often, but still gives me short delays. This is what we end up doing inside the computer, and that's what we'll talk about doing. The alternative, if I have heads or tails, like in the past security case, I could say, well, if you roll 1 through 15, choose heads, they get through. But the other 5, 16 through 20, they are the ones that fail. So this is a way for me to simulate whatever that is, 75 or 80% probability of getting through just by using this fair die. Now, I need a way to generate this fair die, and we'll talk about that in lecture E1. There's ways in which we can use deterministic math to generate something that approximates a fair die. And once we have a fair die, we will then use some mathematics that is in lecture E2 that allows us to draw from any probability distribution we want. So as long as you can go out and fit a probability distribution to data, we can build a sim that generates data that looks just like the real data. And that's what we'll use in these sims. And so ARENA, fortunately, has done the work for us for most of the very common distributions. So in that case, once you know the average of that distribution, or maybe the average and the standard deviation, you just ask ARENA, and it will give you outcomes that are drawn from that. So the inputs to our models are probabilistic distributions. This answers a question from earlier. The outputs are the data. The inputs are not the entities. The inputs are the distributions. The entities are like inside the model. And that's why we're going to use this term input modeling, which is all of like unit G, which is all about how do you choose these probability distributions. How do I choose the probability distribution here, here, and here? That's what we call input modeling. And how do I do it for a much more complicated? Well, I've got more distributions, so I've got more inputs. The entities are the same, but the number of probability distributions change. So the number of inputs. All right, I'll hold questions there, and if you have any other questions, come up to me after class or ask them online. Just reminders. I do have the attendance question I'll have you guys do. These are the same reminders from before. For the attendance question, let's say, when I say the term input modeling, what are the inputs? Just put that in question 1 of the attendance exercise and hit submit. So remember, I said input modeling, the inputs are not the entities. What are the inputs? Again, you're graded for completion, not correctness. If you didn't have if you don't have a device that can allow you to do this, you can write it on a piece of paper and turn it into the after. And if you have any questions, feel free to bring them up. Otherwise, I'll let you guys go.
Again,
The question is, when I say the term input modeling, which is something which is the whole topic of Unit G, what do I mean by input? It's not the entities that are coming into the system. So what is the input when we say the term input modeling? And that's it. Just question 1, and you can hit submit, and that's your attendance for today. And if you've started working on Lab 2, I actually put an example solution set for the hand simulation you'll do in Lab 2. It's available online, so make sure to look for that. It may be very helpful.